Welcome to another higher maths optimization question which involves differentiation. So in this question, a child's drinking beaker is in the shape of a cylinder with a hemispherical lid and a circular flat base. Now the radius of the cylinder, we've been told, is r centimeters and the height is h centimeters, and the volume, we've been told, is 400 cubic centimeters, and that's only for the cylinder part that we can see here. Okay. So firstly, they want us to show that the surface area of plastic A of R needed to make the beaker is this formula here, which we can clearly see once again does not involve H. So let's go ahead and start that part. So I'm going to slide this over a little bit out of frame and do this. So let me straighten this up. So part A here is, well, we know that the surface area will basically involve let me bring this down here a bit closer, the surface area of the cylinder part itself, the surface area of the base underneath, and the surface area of the hemisphere part. And we've actually been told that the curved surface area of the hemisphere is 2 pi r squared. So let's go ahead and make a little equation up which involves all those things. So basically the surface area, which we'll call A of R, is going to be the surface area of the base plus the surface area of the actual circular outer surface of the cylinder, so surface area of the cylinder, and added on to that will be the surface area of the lid, the hemisphere itself. So putting those things together, the surface area of the base, well, that's just going to be a circle, isn't it? It's pi r squared plus the surface area of the cylinder. Well, that's going to be effectively 2 pi r h. And where did that come from? Well, that's the circumference of the circle multiplied by the height, because you can think of the cylinder as, well, if you were to cut a line down here and open it up, it would effectively be one big long rectangle, and the length of that rectangle would be equivalent to the circumference of the circle, and the height, well, that would just be the height. So that's just going to be 2 pi r h plus the surface area of the lid, we've been told, is 2 pi r squared. Okay, so we have an expression for the surface area for this beaker. Now the problem is it doesn't quite look like what they're wanting it to look like. You can see we have a pi r squared here, we have another pi r squared, so we can bring them together to give us the 3 pi r squared. That's no problem there, but the issue is this 800 over r. So what we need to do is find a way to rewrite h here. So let me bring this together. Firstly, so A of r is going to be my 3 pi r squared plus 2 pi r h. And then just off to the side here, I'm going to figure out a way to replace the h. Now they've told me back here that the volume of the cylinder is 400 cubic centimeters. So let's just pop that in there, 400 cubic centimeters. Okay. And the volume of a cylinder, I also know, is the area of the base times the height, because it's effectively a prism. So that's just pi r squared h. In other words, 400 equals pi r squared h. And if I rewrite this for h is going to be 400 over pi r squared, like so. So now I have an expression for h on its own. So what I'm going to do is take this 400 over pi r squared and sub it in for h here. So let's go ahead and do that. So that's going to be A of r is going to be 3 pi r squared plus 2 pi r, open brackets, 400 over pi r squared. Let's go ahead and multiply this out. So A of r is going to be 3 pi r squared plus, well, the 2 times the 400, that's just going to give me 800 pi r on the top line and pi r squared on the bottom line. And you'll notice I can cancel out the pi on the bottom with the pi on the top, the r on the top with one of the r's on the bottom, leaving me with A of r equals 3 pi r squared plus 800 over, and I have 1 r remaining, and that is, let me just double check here, exactly what they were looking for. Yep, perfect, so that's as required. Squiggle that in there. Superb. So that's that bit done. Awesome. Now, that's part A done. Part B was asking us to then find the value of R, which ensures that the surface area of plastic is minimized. Again, this is a stationary point question, whereas before we were finding the maximum area or maximum volume. In this case, we're finding the minimum area or the minimum surface area more specifically, and that corresponds to differentiating this, making it equal to 0, and showing that in fact via a nature table that it's a minimum turning point. So let's go ahead and do this. So if I write down my actual equation once again, so this is part B, A of R equals 3 pi r squared plus 800, and I'm going to write that as r to the minus 1 using my Indus rules from Intermediate 2 maths. You bring the r to the top and the power becomes a negative. Now I'm in a position where I can actually differentiate, so let's go ahead and differentiate this. That's going to give me 6 pi r, and it's actually going to be a subtract 800 r to the minus 2. Excellent. So I have a something I can an expression for a dash r rather, and obviously I have to then make the statement for stationary points a dash r equals 0, hence 0 equals 6 pi r minus 800 over r squared, just taking the r to the minus 2 back down to the bottom. Okay, so what I'm going to do is actually multiply through by r squared to remove this r squared on the bottom line. So 0 times r squared, well that's just 0. That's going to be 6 pi r cubed minus 800. Superb. So I can actually divide through by 6 if I want to, and if I do all that, work it out, then what I'll do is in fact I'll take the 800 over and solve for r. So that's going to be 6 pi r cubed equals 800. So r equals 800 over 6 pi cube rooted, which works out to be 3.5. And I believe the units are centimeters. Yes, they are. So that's going to be 3.5 centimeters. Like so. So I have an R. The only thing is I don't know whether this is a max or a min. I'm assuming it's actually a minimum turning point, and it will in fact be a minimum turning point since this is a positive R squared. But hey, that's not sufficient justification. So we'll do our nature table over here. I'm just going to very, very roughly draw this in here. So that's going to be my R, my A dash R, and of course my shape. And I'm going to do 3.5 here. I'll just put 3 in and 4. And if I plug that into the calculator, so I'm putting this back into the differentiated, I get a negative here, which comes out like that. And I get a 0 here, which is like that. And a positive here, which is in fact a positive gradient like that. So this is my justification to show that it is in fact a minimum turning point. So all I can do is just go therefore for r equal to 3.5 centimeters, in other words, when the radius is 3.5 centimeters, the surface area of plastic is minimized. And that's it. That is what they were asking for, I believe. Find the value of r, which ensures that the surface area of plastic is minimized, and it's 6 marks. So in all, it looks like a pretty horrible question because of the diagram. In reality, it's not too bad. It's not too bad. If you have any questions, please feel free to leave a comment down below. Send me a message, rate and subscribe. It will be greatly appreciated. Till the next time, folks, thanks a lot.